Okay, the famous Greek mathematician Thales traveled to Egypt and tried to measure the heights of a pyramid. And what he measured easily in this given situation was like what is the length of the side of the pyramid, and it was 756. And we don't know what the heights of that pyramid. And at certain time, the shadow of this pyramid was 342 for that. And he used a stick, and the heights of 6 and the shadow is 9 for that. And he used this kind of similarity between two triangles. And we still use this concept in our cases, right? So let's just try to solve this question regarding this way. So let's look at which triangles are similar each other, right? And key point of similar triangles, for example, like that, then the corresponding sides are proportional. Okay? Like this, same ratios each other. So let's look at here. When you look at this triangle, it should be right triangle, and same thing happens for here. Then the ratio between the base and heights in this small triangle is 9:6. Then it should be same to this big triangle. So the height is h, and the base of this right triangle should be half of the 756 plus 342. So half of 756 is 378. So the total must be 378 plus 342. So that must be 720. So the ratio is h over 720 must be equal to 6 over 90. Then from there, the h by cross multiplication, or we just simply saying multiply 720 on both sides, then h must be 6 nines times 720, or 2/3 times 720. So altogether, it should be 480. So by this simple calculation and checking these same ratios, we can measure many cases, which is kind of difficult to do that. What the Thales did was he's the kind of first guy to introduce the logical proof in math. And nowadays, we really kind of follow his method, right? And he actually proved many things. Okay, put here, many. Okay. And one of the famous one is like this one. Okay. The angle inscribed in a semicircle is a right angle. So for any semicircle, so meaning is AB is a diameter, then no matter where this is, if you choose that point, still the angle must be 90 over there. So no matter which point you choose, it should be 90. And actually this concept, this generalization, is a special case of more general case. For any given circle, choose any arc, let's say AB, then you can define two different angles using center. This is central angle for AB, or choose any points over there, and we can get the angle, right? So you can choose this point over there too, but when you compare these two angles, actually the central angle is double of that angle. So if that is 30 degrees, then the central angle must be 60. And that 30 is always same. Doesn't matter which point you choose, right? So if you look at that question from this point of view, let's say what happens if AB is a half circle. So we choose AB like that. And what is the central angle of this arc? Center is here, right? So it must be 180. Then from there, if you choose any C, then it should be half of that 180, so it should be 90. So this theorem is actually a special case of that. So you will see this one in geometry course. But anyway, like that. So the next practice is, okay, let's try to prove. It's like that, right? So one way you could prove is prove that, right? The central angle is double of that inscribed angle. Okay? But we need some more advanced steps for there. So instead of that, you can actually use the isosceles triangle theorem, which says for any given theorem has two congruent sides, then corresponding the opposite angles are also congruent each other, right? And from there, let's look at that case for semicircle for AB. Let's just choose arbitrary point C and make the angle like that. Then all you need is some extra radius over here. Then this should be your arguments. In here, OA, OC, and OBs are all congruent, which means same size. Why? Because they are radius, the radii of this circle. Then when you look at this triangle, OAC, because OA, OCs are congruent, their corresponding opposite angles must be congruent. And when you look at second triangle OBC, by the same argument, like OC, OBs are congruent, their corresponding angles must be congruent. And these two triangles are independent, so these two angles might mostly different than the angle A or something like that, right? But that's the situation. So when you look at this entire triangle, ABC, the sum of these angles, like a measurement of angle A plus measurement of angle B plus measurement of angle C, must be 180 degrees, right? That's one of the statement in Euclidean geometry. Then this sum is actually same as the sum of these four angles, right? So measurement of angle A plus, let me give name here. So that's angle 1 and angle 2, right? So measurement of angle B is measurement of angle B, okay? But measurement of angle C, instead of the entire one, you can break down into angle 1 and angle 2. So that is measurement of angle 1 plus measurement of angle 2. Still it's 180, right? But angle A is congruent angle 1, right? And angle B is congruent to angle 2. So when you look at this one is same as measurement of angle C, right? And therefore, this one must be also same as measurement of angle C, right? You have to explain it, right? In one word. But altogether, that should be measurement of angle C plus measurement of angle C is 180. Therefore, measurement of angle C is 90 degrees, okay? So it's kind of brief, proof, right? So please rewrite with your own word, right? But most likely, the formats of any proof consist of three parts. The hypothesis, you have to state the given condition. It says only a triangle. So in this hypothesis, in this case, you have to just say let triangle ABC is on ABC inscribed in a semicircle, okay? And like AB, with AB is the diameter, right, of the circle. Okay? That's the hypothesis. Next part is body, which is consists of several series of statements, right? So you have to write down this. And the last one is conclusion. So you just restate again, right? Therefore, because of these arguments, we can claim that if the triangle is inscribed in the semicircle, with AB is diameter, then angle ACB should be 90 degrees, right? It's kind of restate these stuff, right? Okay. So that's the typical formats of any proof in math. Okay. So please restate in this way. Okay. Okay. One of the visualization of numbers done by Pythagoreans is polygonal numbers, which means try to matching some diagrams to each integers, right? So 1 is just one dot, and 3 is just three dots, but in certain way, like we see here. And 6, you can arrange the six dots like this, and 10 is like that. So we just keep doing this way. Then there must be some kind of pattern graphically, right? And as a numeral values, right? So let's just try to figure out that. And from there, we can get some famous formulas out of it. So between number 1 and number 3, to get number 3 looks like a triangle shape, and all these are triangle shape. So we call that the triangle number, but 3 is same as 1 plus 2. The reason for that is 1 is defined previously, right? So that is T1 plus 2, right? And 6 is that 3 plus 3, right? Using the previous number here. Okay, this number was here. Okay? So we see the pattern. For 10, the previous number was 6, right? So using 6, then we just need extra 4 there. So we can guess what happens for there without seeing that diagrams, right? T5 must be using the previous one plus one more larger number, right? So 2, 3, 4, 5. So it should be 5 like that, right? So T4 was 10. So T5 should be 15. And we can check this one using these diagrams, right? So previously up to this much, and if you're adding 5 here, then this makes nice triangle shape, and there are 15 dots in this figure, right? So now we found this pattern. So we can say for arbitrary integer n, then Tn should be same as Tn minus 1 plus, when you look at this, T2 is adding 2, T3 is adding 3, and T5 is adding 5. So Tn must adding n there, right? So this should be a nice formula, okay, in one way. But one bad thing about this one is to calculate Tn, we should know what Tn minus 1 is. And to get what Tn minus 1 is, we have to know what Tn minus 2 is, right? So we have to start from the beginning, right? To get anything, right? You cannot get it directly. So the question is, can you find another formula for Tn, for arbitrary n? And we can calculate right away without knowing what was the previous value for this sequence. Okay. So in this manner, when you look at this, instead of looking as a result like that, let's look at starting from here. Instead of saying this 3 is the previous value, what was the previous value? It's actually 1 plus 2. So instead of 3, we can put 1 plus 2 plus the new number here, 3. Then when you look at this, that 6 is same as actually 1 plus 2 plus 3. So instead of 6, we can put 1 plus 2 plus 3 all together and adding 4. Okay? And when we do this T5, we need T4, which is that. So instead of 10, we can say 1 plus 2 plus 3 plus 4 plus 5. Okay, into there. Then now it's very clear, starting from 1 and 1 plus 2, 1 plus 2 plus 3, 4, 5. So altogether, we can figure out that Tn should be just the sum of these positive integers from 1 to n. So now we have two formulas. this one and go further. You know, mathematicians are really lazy people. Okay? So whenever they feel like they have to do a lot of work, then they will not do that. They are looking for some kind of loopholes, right? And some easier way to do it. So when they found this one, yeah, looks good. Finding formula for something is great, but it requires some work, right? Every time. So instead, when they have this one, oh, we don't need to check what is t n minus 1 and t n minus 2. We can calculate, right? But still, what is going to be t 100? Then we have to calculate 1 plus 2 plus, okay, up to 100, right? So 1 plus 2 is 3. We don't want to do that, right? It takes too long. Okay? So mathematicians try to find out easier way to calculate it, and this is the formula. So let's look at here. For example, T100, ooh, it's too much, right? Even using calculators, still you have to punch out many things, right? But if you look at just 100 times 101 over 2, and it's much simpler and easier, right? That is 50 times 101, right? Which means 50, 50. So 5050 is the answer. See, it's very fast and easy. So question is, how can you find it, right? How can you get this formula? And is it really true for any n? And the famous Gauss actually did it when he was 60 years old. It's okay. I mean, it looks like God loves some special people only, right? Okay. So let's just try to find out. The method is like this. He did this one by himself when he was 6 years old, right? And he thought, okay, his classmates really try to do this way, right? They're not looking for a formula, but just to try to calculate, right? So maybe the teacher was kind of didn't want to teach them or want to do something, so just toss out this question to their students, right? So all the kids are just really trying to add 1 plus 2 plus 3 plus up to 100, right? But what Gauss did was, okay, let's say that's the total. That must be a total, okay? And that is 1 plus 2 plus 3 plus up to n. In this case, 100, right? So let's just use that method first. Then let me write down that one again, but as a backward. And I want to add side by side. So on the left hand side is a double of what we are looking for, right? 2 times T100. On the right hand side, when you look at each terms, when you add them, it's always 101, right? And how many of them? 1 through 100. So we have 100 terms. So it looks like, excuse me, 101 plus 101 plus up to 101, and it's 100 of them. So altogether, it should be 101 times 100. So T100 must be 101 times 100 divided by 2. Then we got this result, right? Exactly. Okay, so this method is not only to calculate that special case, we can generalize this entire method. So let's say for any n, for any positive integer n, we can write down that one like this, right? And we write again n plus n minus 1 plus and up to 1, right? So when we add this all together, then 2 times tn is the first one when you add them is n plus 1, right? Plus n minus 1 plus 2 makes n plus 1, right? And last one is simply n plus 1 again, right? So we have a bunch of n plus 1. And how many of them? It's 1, 2, up to n. So there are n plus 1 there. Okay? So the right hand side is simply n plus 1 times n, right? Oh, so let me just write down because it's better. N times n plus 1, doesn't matter. Therefore, the triangle number t sub n is n times n plus 1 over 2. And that formats are everywhere, right? No matter how you look at it. So that should be the formula for the triangle number. And in this practice, we could check that the simplest formula for triangle number using graphs, right? So T sub n means the number of dots, right, in that triangle shape, right? So no matter how many of them. And 2 times T sub n means we just put these two triangle or the triangle shapes of a collection of points, right, together, right? But when you place them, if you place them nicely, like this, and just kind of push a little bit, then actually you can arrange our triangle in this manner, right? Then when you look at that triangle shapes, if it's a T sub 2, then we have 2, right? So you can place your triangle in this way. If it's T sub 3, then we need 3 dots like this, right? So 3 and 3 like this. So when you're thinking about this way, we have n dots there, right? And the height must be also n dots. And we put the same triangle shape of dots above it, right? So not increase in this way, it's just one above here. But because of the shape, we adding one more line over there, right? So we still have n and n here. But when you look at entirely, it looks like rectangular shape. The base has n dots and the height is n plus one more line, right? So it's going to be n plus 1. So 2 times Tn is actually n times n plus 1 dots there. So we have to divide by 2 both sides to get it, right? So as you can see here, you can explain that, right? So please give me that explanation here.